Hey there, Calc folks, back here with another lecture in my series of lectures in our study of vector-valued functions, where in this lecture I'd like to spend some time looking at, I'd like to spend some time looking at curvature, the property of curvature along these vector-valued functions. As we know, the vector-valued function in R sub n represents a path or a hyperpath in R sub n. And along that path, we say it's a curve, so it has this aspect of changing direction as we move forward in our values of the parameter, right? And that change in direction can happen rather dramatically, or that change in direction can happen rather gradually, right? And how quick, right? How quick we change direction along the curve describes what we call curvature, right? If we actually get into the notes here, we will see that is what we have set up in our definition here, right? Excuse me. Given a curve, R bar, in our n-dimensional space, along the curve, at every point where there's going to exist this property of the curve known as the curvature of R bar, right? The curvature is actually a scalar value. It describes a scalar, or it's described by a scalar value. It is not a vector value description. It is just a scalar value, a single numerical measurement, right? It describes curvature. Excuse me. And we denote it as the symbol kappa. It looks like a little K there, but that is a kappa. Where what kappa describes, folks, what curvature describes, is, like I said, how quickly we change direction. And the way we go about summarizing how quickly we change direction is by looking at the rate of change in the unit tangent vector along the curve. All right? We're not so much cared about direction of that change, but what we are cared about is how quickly it is changing. All right? This is the definition of curvature seen as follows, right? And if I scroll that definition up into play, right, what we do note is given a smooth parameterized curve R bar equal to R bar of S in R sub n, right, which is the vector valued function R bar defined in terms of the arc length parameter S, the curvature of R bar, right, is described by, again, what we said is the rate of change in the unit tangent vector with respect to a change in a length along that curve. We move a certain length, how quick is that unit tangent vector changing, right? And is given by the scalar valued quantity seen below here. It is given by this scalar valued quantity, right? Kappa, our curvature, is a magnitude calculation, right? It is the magnitude for what is the rate of change, right? The first derivative in our unit tangent vector t bar expressed within the context of the arc length parameter S, all right? It is the magnitude for this rate of change value, right? This rate of change in the unit tangent vector with respect to arc length parameter. Where when we think about t bar, right, t bar in terms of S, the unit tangent vector in terms of S, it is, right, calculated with the defined value for unit tangent vector, right? The defined value for the unit tangent vector says, well, t bar of t is just where t is any parameter, is just the derivative of R bar over the magnitude of that derivative, right? And S is any parameter. Specifically, it's the arc length parameter, but it's also just any parameter, so it follows from a similar calculation. It is R bar prime of S divided by the magnitude of R bar prime of S, right? And this corresponds to the unit tangent vector for R bar with respect to parameter S, right? And note, in comparison, larger values of kappa indicate a greater amount of curvature. Larger values for our measurement of curvature, the scalar measurement, indicate a greater amount of curvature. And we are just looking at the rate of change in this unit tangent vector's rate of change. Not so much interested in the direction that this change is happening, although that is going to be the next aspect, but it's going to be described by what we call the principal unit normal vector, right? What we're really interested in, how quickly is it changing by, right? And that would be the rate of change or the magnitude given by that first derivative vector. Right? We might consider the description for the curve r bar of s equal to s comma 1/2 s squared. Excuse me. Got a bug in my throat in this lecture, and I have started, so I'm not going to stop. I'm going to suffer through this. All right. For r bar equal to r bar of s, right, our first derivative, r bar prime of s, is just going to be, right, we can go through the derivative rules here applied to this vector valued function, and it will just be 1 comma s, right? We see that as the first derivative, and if we take the magnitude of that and describe it, it is the square root of 1 plus s squared, right? And if we arrange that into a ratio, putting this vector over this its magnitude, we will prepare the unit tangent vector's description, right? We will prepare this value t bar or t bar of s. Right, the description of the unit tangent vector with respect to s. Right? And it's going to be given by this here. Right? This component 1 over this square root, the component s over the square root, respectively. Right? Where if we take the derivative of that, now I did use a little Mathematica to calculate through this, and I did not put this into the work. If you were to go through this, you could set it up a couple of different ways. You might go with a little quotient rule and chain rule. That derivative would involve a little chain rule in its calculation. Or you could rely on a little product rule and chain rule if you were to rewrite your denominator as a product with a reciprocal function, right? With a reciprocal of the denominator. So, there's a couple of ways to approach these derivatives. I went ahead, you should know how to find derivatives, right? I am going to show you chain rule in the next chapter, which is going to help you calculate these derivatives a lot quicker if necessary, right? And a way to organize all that. But I did calculate these out on Mathematica, and this is our respective derivatives, right? This is the derivative of the first component, simplified, and this is the derivative of the second component, simplified. Right? Implying, by definition, right, our curvature, right, is going to be the magnitude of this vector seen above. Where if I go off and I calculate the magnitude of this vector with Mathematica, and I did go over and do that, right, I am just going to take the square root of the sum of these components squared, and through some simplification, you can certainly see how that s squared become 1. There might be some canceling with some 1 plus s squareds down below. This is actually going to be to the 3/2 power. So if that's raised to the 3/2 power and you square that, it's going to just be to the 3rd power. So it simplifies along the way. And you can get that all to simplify down to 1 over 1 plus s squared. And this is our description of curvature. It's a scalar value. It's a scalar valued function. Right? Thus, the curvature of r bar of s, right, is described by this scalar valued function. Notice kappa is not given the vector notation, right? We don't see that vector notation on there. That's not proper because it's not a vector. And that's what confuses students is they forget to take the magnitude here at the end. It's the magnitude of t bar prime of s. Right? So make sure you're taking that magnitude calculation. All right? But this is a scalar valued function that describes the curvature seen along this curve at any value of s, at any value of the arc length parameter s. So if we plug in 0, we can certainly see that's going to be 1 over 1 plus 0 squared. That will be 1 over 1, which simplifies to 1. Right? If we were to plug in 1, right, we would have 1 over 1 plus 1 squared. 1 squared is 1 plus 1 is 2, so you'd have 1 over 1/2, right? We see these results here respectively. So what does that tell us? The curvature along this curve at s equal to 0 is 1. The curvature along this curve at s equal to 1 is 1/2. Meaning that there is more curvature on this curve at the value of 1 than at the value of s equal to 0 than there is at the value of s equal to 1. Right? In terms of our description of curvature there. Right? And if we actually look at the illustration, here's the illustration of our curve where I have indicated in this illustration where s equals 0 and s equals 1. Here's where s equals 0, where the curvature is considered to be 1 in value. And here is where s equals 1, where the curvature is considered to be 1/2 in value. And what you can note is along this parabolic curve, yes, at the vertex is where you're probably going to see a greater amount of curvature, and in fact is where you're going to see the greatest amount of curvature. And as we move away from that vertex or on that parabolic curve, our curvature is certainly going to decline. It's going to decrease. And we do see it decline to 1/2 when we're at the value of s equal to 1. Right? Certainly the amount of curvature seen here is less than the amount we're curving seen here. Right? And that measurement of curvature is indicating that in value. Right? Now, I have shown you how to define R bar in terms of s when looking at the arc length function. It does give us that relationship between s and t, where we can solve that for t and replace that argument in terms of s in for t into r bar of t and get r bar of s. But to avoid having to do that in our curvature calculations, there is an alternative calculation that we can use on the vector valued function r bar equal to r bar of t. And that's what we see that follows here, is this alternative calculation for just the case of calculating the curvature of r bar of t, where r bar is defined in terms of any parameter t, not just arc length. And to go about doing this, we just note, to determine the curvature of r bar, I do go through a little bit of proof of where this formula comes from. Recall from the chain rule for vector valued functions, if I think about the quantity given by the derivative with respect to t, the unit tangent vector with respect to t, it is the rate of change in the unit tangent vector with respect to s times ds dt, right? If we think about t equaling some function of s, right? We might note from the chain rule for vector valued functions, right? Oh, we should say here, letting s equal some function of t is how we might say it here. The rate of change in the unit tangent vector with respect to t is really the rate of change in the unit tangent vector with respect to arc length, right, times the rate of change in the arc length with respect to t. This being a vector value description times the scalar value description, where s equals s of t. All right? This coming from our arc length function. Let's make note of that. The arc length function. We can draw this result out initially from chain rule of vector valued functions, implying that d of t bar of ds, right, this quantity seen here, is really just equal to this quantity divided by this quantity. If it's the product, we can write it as the quotient, right, respectively for d of t bar ds, the rate of change in the unit tangent vector with respect to s. Right? Where we can even go further now and note, where since when we think about speed being the value ds dt, the change in position or arc length, or change in position or length with respect to time t, right? 60 miles per hour. 60 miles is our change in length. Per hour is our change in time, right? That's speed, which would be equivalent to the magnitude of our velocity function. We understand that from motion in space, where since velocity is really just our first derivative of r bar prime of t, we could say is equivalent to the magnitude of r bar prime of t. Where since speed is equivalent to this, I can go into this calculation for ds dt that I'm dividing by here and really think of it as taking that numerator, the derivative of the unit tangent vector with respect to t times the reciprocal of the denominator, or the reciprocal of the speed, right? Which will prepare this quantity here. And I should make that a magnitude calculation here because it is direct in this. What am I doing? In this calculation, right? Because ds dt is equivalent to that, and that's what we're replacing it with. And then we come back in when we think about then kappa, right? The measurement for curvature being the magnitude of the unit tangent vector with respect to s being equivalent to this statement here, right? The magnitude of this is going to be the magnitude of this times the magnitude of this. Now, the magnitude of this, that's an absolute value. There would be the absolute value of this times this, and that is already calculated with its magnitude in that calculation, all right? Whereas we would apply the magnitude to this aspect, right, and have the magnitude of the unit tangent vector with respect to t, where that is just t bar prime with respect to t, right? And since this is all equal to just the magnitude of r bar prime of t, right, we could just divide the value t bar prime of t's magnitude by the magnitude of r bar prime of t and come up with our result. And this is the formal result we see given by definition here, folks. All right. Given r bar equal to r bar of t and r sub 3, a smooth parameterized curve where t is now any parameter. It could be arc length, but any parameter works, right? Then the curvature of r bar with respect to any parameter t is given by what we see here, right? The above result. This calculation seen here in the end. All right? The magnitude of the unit tangent vectors, first derivative with respect to t divided by the first derivative of the unit tangent, or of the vector valued function r bar with respect to t. First derivative, if I said that in there. All right, there's a lot going on in that calculation. Let's set it up. All right, consider the curve given by the vector valued function r bar of t equal to 2 cosine t comma 2 sine t. All right. We're going to need r bar prime of t. It is going to be used to calculate t bar of t. It is going to be used to calculate t bar, the unit tangent vector, right? But it's also going to be used here, right? So if we go through and we calculate that, it would be negative 2 sine t, 2 cosine t. And if we think about, we are going to also need its magnitude. If we set that up in calculation, this is kind of a unique case, right? Due to the description of our first derivative involving sine and cosines in each term, squaring those is going to bring in a sine squared of t plus a cosine squared t, where when we factor out the 4, we're left with this quantity here where we know from the Pythagorean identity all that's equal to 1. So this is the square root of 4 times 1, which is equal to square root of 4, which is 2 in value. And we get a nice clean result for this magnitude calculation. So the denominator in our description of curvature in this format is going to start with just 2. It's going to be constant. Furthermore, if we take r bar t and divide it by its magnitude, we do get the unit tangent vector t bar of t. So this is what you see going on here. This is r bar prime of t divided by its magnitude. And if we divide by 2, we divide out the 2's from r bar prime of t, and we have just negative sine t comma cosine t as our vector description. All right? Applying, if I take the derivative of that from our derivative rules, that's just negative cosine t comma negative sine t. Right? And the magnitude of that is going to, again, now be the square root of cosine squared t plus sine squared t, where we can see through that Pythagorean identity again here, that's equivalent to 1, right, underneath the radical. So we have the square root of 1, which is also equivalent to 1. All right? So the numerator in our curvature calculation is also going to be constant at the value of 1. All right? And if we arrange that numerator's constant value of 1 over the denominator's constant value of 2, we get the scalar measurement for curvature here, folks. All right. Thus, for the vector valued function r bar of t equal to 2 cosine t to sine t, the curvature is a constant, right? Let's say it this way, is the constant scalar value given by the following here, right? Kappa of t, right? This function of t is equal to 1/2 a constant function. The constant scalar value function given as follows, right? Typically, we expect a functional relationship here. It's kind of a unique case that we've gotten a constant. We've gotten a constant function, right? Regardless of what location or value of the parameter t we substitute in along this curve, we always see this constant curvature. And you might imagine it, or at least take note of what is the shape of this vector valued function. If I scroll down here, you can see it come into view. Here's the description of this vector valued function. At t equal to 0, we start here, 2, 0, and we move around the curve in this orientation, in this counterclockwise orientation. Right? And the curvature we're experiencing is constant. Right? The rate of change in our direction with respect to the length that we're moving along that curve does not change. It remains constant. Right? It remains constant in value at 1/2. Right? So, all right, we are looking there at this case for the case of a constant curvature. And if you have constant curvature, you actually have the case for a circle, folks. All right, take note. That is kind of the uniqueness of this case. Now, there is one third additional case we take note of, right? There is an alternative that actually relies on, and I don't give proof of this. I don't give proof of this. You could take proof. I think the proof is given in the book. But here's an alternative calculation. Given r bar and r sub n, right, where the first and second derivatives exist, right, the curvature of r bar is actually described by this calculation also seen here, where it's the magnitude of the cross product of r bar prime and r bar double prime divided by the magnitude of the value given by r bar prime quantity cubed. And this is a formulation that works nice if you're given a description of velocity and acceleration, folks. If you have a description of velocity and acceleration, right, this calculation also often works very nice with coming up with a description of curvature absent, right, absent a position description, right, which is sometimes the case, right, which is sometimes the case. For example, suppose the velocity of an object at time t in r sub 3 is just simply described by v bar of t. With that little bit of information about velocity in my motion in space problem, I can use that to find my description of acceleration, r bar double prime. This, what I'm given is r bar prime. I can find their magnitudes, right? Find the cross product of the magnitude, or the magnitude of the cross product. Find the magnitude of r bar prime at t, cube it, and arrange them into this ratio. And I can come up with my description of curvature here. All right. Note, we take note, what is acceleration? Well, first derivative is going to be the vector 1, 1, 0 for v bar of t. Derivative of this first component is 1. Derivative of the second component is 1. Derivative of this constant for the third component is 0. All right, respectively. If we now cross those, remember the cross product sets itself up as this determinant calculation. All right. Where this first component comes from t plus 2 times 0 minus 3 times 1. All right, so that is just negative 3. This second component comes from 3 times 1 minus 0 times t minus 1. That's 3. And this third component here, right, comes from t minus 1 times 1 minus t plus 2 times 1. So that's t minus 1 minus t plus 2. Where when we simplify that, the t's cancel and we're left with negative 3 in value. So here we have negative 3, negative 3 is our cross product of the velocity and acceleration vector in this case. And that does lead us to the magnitude of that being a constant description. constant scalar value 3 square root of 3, where that is going to be the numerator in my description of the curvature, kappa. And if I then think about the magnitude of my velocity vector, right, we're going to need the cube of that in the denominator. Well, that's going to be my velocity vector's components squared and summed, right, and placed underneath this radical. Where if I expand these using, realize that's an a minus b and an a plus b form. This is a squared minus 2ab times b squared. This is an a squared plus 2ab times b squared. This is not just t squared minus 1 squared. This is not just t squared plus 2 squared. Remember, these are a minus b squared and a plus b squared forms. Big mistake students often make there. But if we expand all this out, we do get this nice quadratic, simpler looking quadratic underneath our radical, where when cubed and placed underneath this quantity will give us our description of curvature, right? So for our description of curvature, placing that magnitude calculation in the numerator here, right, and putting it over the magnitude description of our velocity function cubed, we prepared this description of curvature, folks, in terms of the context of parameter t. And all we started with was our description of velocity here, folks. Right? An interesting way to go about setting up a curvature calculation. Notice I did this one for a curve in three-dimensional space. This is actually a little bit of a, I believe, well, I'm not going to say projectile motion because the way it's set up, it's not quite. Right, folks? But nonetheless, it is a velocity problem where you can find acceleration and use velocity and accelerations descriptions to come up with a description of curvature along that curve, right? Which means velocity and acceleration are somewhat related to curvature, which makes sense, right? Velocity is how quickly we're moving forward, right? And what direction we're moving forward when we're in n-dimensional space. Acceleration, we've said, is a summary of how much we're turning, right? How much we're changing in velocity, which is a summary of how much we are changing in terms of going forward and how much we're changing in terms of going orthogonal to that direction, right? How much are we going forward and how much are we going orthogonal to that direction, right? We have this acceleration description that summarizes both of those changes in velocity. So that means acceleration and velocity will probably be related to curvature, and they are, right? We see through this result seen here. All right. What we have to come back to also, folks, is, like I said, this is just how quickly we are turning. What might be of interest to us is actually the direction in which we're turning, and that is going to become about from the principal unit normal vector. That's our next video here. Take note of that. You'll want to head off in the principal unit normal vector. And then, like I said, velocity and acceleration are somewhat related to curvature, right, through this formulation here. So we're going to come back and look at those, being able to use curvature and be able to use our descriptions of velocity and acceleration to develop a formulation for how much of our acceleration is in terms of change in speed and how much of our acceleration is due to a change in direction, right? Those two orthogonal components of acceleration, right? We'll have an understanding of unit tangentness that comes in from, we talked about the unit tangent vector previous. We're going to develop an understanding of the principal unit normal vector, which is our description of how much our direction of the turn, right? We'll have forward, we'll have direction of turn, and once we have the summary of those two, we can kind of break down that summary that comes from our acceleration vector. Right? Can I do that with 3 fingers? Right? We'll come up with that acceleration description there in all that, folks. That is where we are certainly heading with these ideas. All right. But I hope you're hanging in there. We're about a 30-minute video here. We do present a couple of calculations. I do it in 2- and 3-dimensional space with illustration, folks. Keep in mind, curvature is a scalar valued function. It is not a vector description. All we're really interested in is a magnitude or a size there, folks. And it's a property of the curve. It's how quick is that curve changing its direction with respect to a change in length along that curve. That's curvature. All right. So with that said, I'll end this video, get it posted, and we'll be on to talking a little bit about principal unit normal vector, folks, and how that calculation is done. That's a quick video, and then we'll come back to components of acceleration. All good things, folks. I'll see you then.